This episode is going to look at sketching modulus functions and using these sketches to solve inequalities. First, let's look at the definition of modulus or absolute value. It is important to think about the absolute value of a number as its distance from the origin, rather than just it makes the number positive, as we can apply this definition to complex numbers too, so we don't have to learn separate definition or method of finding the absolute value in different situations. First, we will look at how to sketch a modulus function. To begin with, we want to sketch the function inside the modulus and then perform a transformation. As discussed in episode 1, we will first consider the asymptotes. The vertical asymptote will be x equals 1, and the horizontal asymptote will be y equals 1. We will also find the y-intercept to inform which quadrants to sketch each part of the function. Please go to episode 1 for more information on this process. Now we can look at the transformation. The absolute value will have no effect on the positive parts of the graph, as the y-coordinates are already expressed in terms of their distance from the origin. The transformation will affect the coordinates with negative y parts. As y-coordinate of negative 3, for example, will be transformed to positive 3, as negative 3 is a distance of 3 from the origin. In effect, this point is being reflected in the x-axis. This will be the same for each of those coordinates, resulting in this whole part of the graph being reflected up. By finding the x-intercept, we know exactly which part of the graph this is. It is therefore the part where x is between 1 and negative 1. In effect, this function has been split into two parts. When x is less than negative 1 and greater than 1, the function remains the same. When it is between 1 and negative 1, it becomes the negative of the function as it has been reflected in the x-axis. We can, therefore, form this piecewise representation of the function. This will be important when forming equations, or as you will see in future episodes, when using calculus to find gradients and definite integrals of modulus functions. Now let's look at using the graph to solve an inequality. Adding the line y equals half, we can get an idea of the answers we're looking for. This is why it is important to have a sketch of the function, so you can be assured the inequality you end up with represents the part you need. If you are just trying to solve the inequality without the sketch, then you are doing so blindly. The biggest piece of advice I give is to use diagrams, where appropriate, to solve questions or to get you started, as they help to inform solutions. Firstly, we can see that x is greater than 1 is an obvious solution. Secondly, we can see there is an intersection with the graph when x is less than negative 1 and when x is between negative 1 and 1. We can find the first intersection by forming this equation and solving. We can find the second intersection by taking the negative of the original function and putting it equal to a half, as we can see that the second intersection is in the second part of the graph. We can now form our two inequalities that we can see on the graph. Notice how x is less than 1 but greater than minus 1 over 3 is separated from x is greater than 1, as we need to keep x equals 1 out of the solution, as it is not part of the domain of the function. You should be careful about inequalities, especially where fractions are involved, as you don't know when you may be multiplying by a negative. It is much easier to find intersection points and then use the graph to inform you of the inequality answers. You don't need to worry about inequality signs changing direction if you use this method. In the next example, I know this is not a rational function, but it highlights why the sketch is so important. First of all, I will find the x-intercepts of the quadratic, and I know the y-intercept is negative 3, so that I can sketch the graph. Next, I know that the negative part of the graph will be reflected in the x-axis as previously discussed. However, before I put in the line y equals 3.5, I need to know whether this goes above or below the maximum point of the graph, as, although it is a sketch, All sketches involving more than one graph must have them sketched correctly relative to one another. There are several ways to find the maximum or minimum of a quadratic, but I'm going to use the method of finding the x-value of the coordinate by knowing that it is halfway between the roots of the quadratic because of the symmetry of the graph. This is when x equals -1, and gives me a y-coordinate of 4 when it has been reflected in the x-axis due to the modulus. Therefore, the line will come below the maximum point, and I can see there will be 4 points of intersection, 2 with each part of the graph, the original quadratic and the negative of it. I will start by solving the original quadratic equal to 3.5, making the coefficients integers, and I can't factorize, so I'll use the quadratic formula. As this video is not about solving quadratics using the quadratic formula, I will skip to the simplified roots. I can now use this sketch to form my two inequalities relating to the regions where the original function is greater than 3.5. I can now do a similar thing, but this time setting the negative of the quadratic equal to 3.5 and solving. I can see this relates to one whole region, so my solution is x is between -2 minus root 3 and -2 plus root 3. I want to emphasize this diagram is integral to the solution, as we need it to conclude that there is this extra region in the middle. You can think about what might happen to the quadratic equation if there were no solution in this part. Finally, to finish, let's have a look at a different type of modulus translation. Instead of the modulus of the whole function, we can look at the function of the modulus of x. We will start again by looking at the original function with no modulus, then look at h of modulus of x. In order to understand the transformation, let's again consider some coordinates. Firstly, substituting in x equals 1 will not have any effect on the coordinate, so it stays the same. We can see this will be true of any positive value of x. However, when I substitute in x equals -1, I will get the same y-coordinate as when x is equal to 1. The same thing will happen with 2 and -2. I could repeat this with all positive x values and their corresponding negative values. Therefore, we can conclude that when x is positive, nothing changes, but when x is negative, the graph is a repeated version of the graph when x is greater than 0. This gives us the following graph, where we can see that even the vertical asymptote will be reflected, thus excluding another value from the domain. We can see this also has an effect on the range, where there is no part of the graph for when y is between the horizontal asymptote of y equals 1 and the y-intercept. If we find the y-intercept by substituting in 0 for x, we can find the range of y is greater than 1 or less than -1. Let's finish with another inequality related to this graph. We can see there are two intersection points with y equals 2. We can equate the original function to find the intersection point for when x is greater than 0, as this part of the graph remains unchanged. We get x equals to 3. Although we could form an equation by substituting in -x to find the intersection when x is less than 0, we can see, by symmetry, the solution must be x equals to -3. I can now form two inequalities of x is less than -3 and x is greater than 3. I can also see that the middle part of the graph should also be included when x is between the two asymptotes, giving my final inequality of x between 1 and -1. I hope this video has helped give you a method for solving modulus inequalities by sketching their graphs. I also hope it has highlighted the importance of diagrams to inform solutions.